fuck if it was off. Hey, what's going on? Welcome back to Structurefree Office Hours. In this video, let's see, we're gonna talk about torsion, all right? And we'll just do a example on torsion in our office hour session here. So the first thing, you know, you'll be given a problem. It's like in 3D, right? And so, well, in this problem, I'm given some sort of rod that has a bunch of torsional loading from, let's say, a bunch of gears connected to it. And it has a diameter. It's a solid shaft. It has a diameter of 40 millimeters. And I want to find the absolute maximum shear stress, tau max, along the shaft. And then it says I want to draw the shear stress distribution. Draw shear stress distribution. And maybe we'll even draw a differential volume element. So I'll show you what that means, like drawing a differential volume element. But that's not essential right now. That's going to be more important when we do like, what is it? Like stress transformation and things like that. Okay, let's see. So the first thing is to interpret usually a 3D drawing into a 2D torque diagram. Okay, so here's this is schematic. Oh, dude, what is my thing defaulting? Schematic and slash FBD here. And here, is there a way I just default to pen? Touch. Interesting. Okay. And so here I will stand as an observer here looking at this. So A will be on the left, and this is what the rod would look like. Okay, and I'm not going to draw the gears in, but I'm going to draw the concentrated torques. Okay, and let's see, the first one is if I use the right hand rule and I curl my fingers in the direction of the arrow, at point A, it's applying 15 Newton meters at A. And then at point B, I have, whoa, why is it defaulting to this? This is B. How many letters? I have C, D, E. C, D, and E. C, D, and E. And let's see, E is curling into, so this would be here, would be E at E of 70 Newton meters. And then B is curling out of the page, so this would be 25 Newton meters. And then C is curling into, so it'd be 30 Newton meters, and D is curling out of, so it would be 60 Newton meters. Okay, and what's really convenient about this is that it's the, you know, the analysis process is just like axial loading, except we have twisting moments or torques. And so I would go through and identify discontinuities and cuts. Okay. And so here I would based on this, I have a bunch of concentrated loads or moments. So one, you're gonna get dizzy when you watch this later. Two, let's see. Hey, what is up? The pen is giving me problems.
Are you pressing a key on the
other wonder. Side? Oh, maybe that's a good point. Oh, I hope. Oh, maybe you're right. Thank you.
Does that fix it?
I hope so. Let's see. C. Oh, snap. Okay. Let me put it on the ground. Let's see what happens. D and E. I wonder if it's my touch in here. Okay. And so I have 1, 2, 3, 4, 5 discontinuities to determine all. There's basically in between is where I need to determine all my internal loads. So I would have, I have in a way, I have to cut this 1, 2, 3, 4 times to do this problem, right? 1, 2, 3, 4, like this. Are you good, or you just have to go?
Yeah, I'm good. Yeah, I got you.
Okay. Let me know if you have more questions. Okay. All right.
Sir.
All right. And then, so I have 4 cuts I need to make, and so I'm gonna go ahead and determine the internal loads. Okay. But I'm gonna give myself some space here, right here. Okay. Because I'm gonna draw for us what I would call the internal torque diagram. Okay. The frick. Okay. So I'll draw here, and to draw this internal torque diagram later, I'm gonna have. I would draw, just like shear and moment diagrams, this would be an internal torque diagram in Newton meters. And I will tell you that, like, what we have to do is draw vertical lines at discontinuities. I think I need to wear a glove. I seriously am going to wear a glove. Okay. And so here, this would be B, C, D, like that. Okay. Those will, okay. And we basically have to determine the internal loads between those vertical lines. All right. So 2 would be internal loading. And I think if I show you one, you'll get the rest. But so for internal loading here, I would have, like, let's say I do cut 1, right? Cut 1. And I draw cut 1 like this, and I look at the left side of the cut, and I draw my favorite. This is the external load, the 15 Newton meters, and then the internal load, I'll call that my torque here, TA B, like this. And then I would apply equilibrium, and this equilibrium would be sum of the torques. Right here. Let's see, is there something I can do? Oh, okay. I wonder if that might. Okay. Will that help me? The sum of the torques equal to 0 when I apply my equilibrium. And I'll say positive torques are the double arrows pointing to the right or curling out of the page. And so in this case, it would be TAB plus 15 Newton meters equals 0. And this would tell me my internal torque is negative 15 Newton meters. Okay. Then so that's it, right? And then I do cut 2. And for cut 2, I would make the cut at 2. I draw everything on the left or the right, doesn't matter. Okay, left of that cut, I do 1 cut at a time. Okay, so it's not like I'm making 2 cuts. And this would be TBC. And just like axial loading or a normal force, I draw away from the cut is my positive internal sign convention, right? It's my away from the cut, or is that torque is the one that's positive internal torque. And I would have a 15 Newton meter here and a 25 Newton meter here. Those are my external loads. And again, I would apply sum of the torques equal to 0. I'm going to say positive is to the right. And this would tell me TBC plus 15 Newton meters plus 25 Newton meters equals 0. And this would tell me TBC is negative 40 Newton meters. Yeah. And then I can go ahead and do that for cuts 3 and 4, right? And from cut 3, I would get, I don't know, do you want me to do it, or you feel like?
I feel good.
You feel good?
Yeah.
Okay. So if you want to try, I'll tell you right now, cut 3, the TCD should be negative 10 Newton meters, and then TDE is negative 70 Newton meters. And I could actually draw a torque diagram, an internal torque diagram here. So here, this would be like, I know between A and B, my internal torque is constant. So it's just going to be a straight line. This would be like negative 15 Newton meters. Mm-hmm. And then between B and C, it's also constant, and it's negative 40. So I write like negative 40 here. And then between C and D, it's negative 10. So I write negative 10. And then between D and E, it's negative 70. Negative 70 right here. Okay. And this would be an internal torque diagram. Okay. It tells me all the internal torques through the entire length of my structure. All right. Okay. Mm-hmm. All right. So now we have to calculate the stress. If we didn't know what we were doing, we would calculate the stress at every single location for every internal load, and then compare and choose the absolute max, right? So we would have to repeat that calculation 1, 2, 3, 4 times. Mm-hmm. But we do know a little bit, right? We do know 1, 2, 3. We want to do our stress calculation. Stress calculation. We're trying to calculate the absolute maximum shear stress. And so we know that tau, the shear stress due to torsion, is this T rho over J. Okay? And J is a geometric property. Rho is a geometric property. And then torque is the thing that's kind of varying, right? Mm-hmm. So here in my cross section, if I look at the cross section of this shaft, my diameter is 40 millimeters. And so, I have the center here. Based on the cross section, where is my maximum shear stress?
On the outside.
On the outside. So for rho, I'm going to use the largest rho I can use, and that's going to be
the radius.
The radius, which will be 20 millimeters. So in this case, that would be here, somewhere on the outer surface. Okay. Mm-hmm. And then J is constant. All right. So to get the max, I'm going to use a rho of 20 because I want to be at the outer surface. Mm-hmm. And then J, because it's a solid circular shaft, will be pi over 2 times the radius, 20 millimeters, to the 4th. Okay? Mm-hmm. Then I have to look at my internal torque. So which segment should I look at? Should I look at the negative 15, the negative 40, negative 10, or negative 70 segments?
Negative 10.
Well, which one will give me the largest shear stress?
Negative 70.
Negative 70, right? Yeah, the largest torque, because it's not inverse, it's directly related. Mm-hmm. So then my tau max here, my absolute tau max. So the negative just indicates the direction, and we'll talk about that in a second. But here the max, so I could put absolute values because I'm looking at absolute max right here. So this would be 70 Newton meters times, I'm using millimeters and millimeters, so I'll just go ahead and convert the meters into millimeters right now. Mm-hmm. So that would be 1,000 millimeters per meter times the 20 millimeters divided by pi over 2 times the radius to the 4th. 20 millimeters to the 4th, like this. And then this, and I let's calculate it real fast. Let's just calculate that. Let's see, 20 cubed, 70,000. We get 5.57, and if we did our units right, it should be Newton per millimeter squared, which is the same as a megapascal. So this is 5.57 megapascals. Okay, and so that is my absolute maximum shear stress. Okay, now check this out. Okay, so that's one answer. That answers something for us, which is great. Okay, now here, if I look at cut 4, so imagine I have here. Let me use my marker here. I'll use this right here. Okay. Mm-hmm. So here is cut 4. Mm-hmm. Okay. So here's the rod. Here's cut 4. Mm-hmm. I cut it. Mm-hmm. Okay. I take it off the page And now we're looking at it. You're looking at the face of the cut.
Yeah.
Everyone agrees, right? Okay, so good. We're looking at the face of the cut. Okay, so this is for the stress distribution. 1, 4, stress distribution, the drawing that we're going to use. Okay, so I cut at 4. I pick up the rod. I look at the face of the cut, and this is what I see. So draw another circle. Okay, and the torsion is negative. So what is the direction of the torque? Or the torque is negative. So what's the direction of the torque? Is it going into or out of?
Into the page.
Into the page. Great. It's going into the page, which means the torque is this way. Okay, it's going into the page. I curl my finger. So on this one, it would be going clockwise. But basically, it means I'm smearing my bagel in a clockwise direction. Okay? All right? All right, good. And then here, now the question is, can I draw a stress distribution on any radial line? So here, if I just choose, we'll start with simple one. I'll just draw a horizontal radial line, right? And can I draw, so at the stress distribution in red, at the center, what's my stress?
0.
0. And at the outer surface, it will be?
5.57.
Perfect, 5.57. Okay, so at the outer surface, it'll be 5.57. Is the shear stress pointing up or pointing down in this case?
Up.
What's the direction of the torque, the internal torque?
Oh, down.
So it would be pointing down.
Yeah.
So the stress is going to go in that direction of the torque, the internal torque. And then boom, this will be 5.57 MPa, like this. And then I would draw, it's linearly varying. Because, this T rho over J is linear with respect to rho, right? And so then I could just draw the other arrows like this. Okay? All right. Okay. And this distance right here is the 20 millimeters. Yeah? Okay. If I asked you, what the heck is the shear stress? What is the shear stress is right here. If that distance is 10 millimeters from the center, what would you say that is?
Half of 5.57.
Exactly, half of 5.56, because it's linearly varying. I could do similar triangles. I could also just go back to this equation and replace the 20 with the 10, and that will give it to me. So this would be half of 5.57, whatever that is, right? 2.285 maybe? Yeah, 2. It's all good. Okay, so I can do that for any point on this radius. That's nice and convenient because it's linear. Okay, so good. And in fact, so if I asked you, like, can you draw the shear stress distribution on this line here? Could you draw that?
Yeah.
Go for it. Just draw it. Let's draw it. I'll draw it too.
Okay.
Okay, I'll use the same. Okay. All right. Yeah. Good. Yeah, so all our stress arrows are perpendicular to that line. The dotted line being horizontal is just coincidence.
Yeah.
Right? But it just, boom. Okay, and that at this surface right here, that stress is 5.57 MPa too. Okay, great. Great. So the differential volume element is so if you can imagine, I can cut the entire, I can cut off everything around this point. Okay, I can keep cutting and cutting until I have one single little differential cube, a little cube left. Okay, who cares about the word differential? That's just a little itty bitty cube. Okay, and because my structure is in equilibrium, so is every itty bitty little cube, like, here on my structure, right? Every single one. So if I could cut out one of these cubes, let's say this one right here, I know I drew it like outside, but let's just say it's within the radius. It's so small, okay? So this cube would look like this in 3D. It would look like this. Right here, this is the face of the cut. This is a cube at the outer surface. It basically represents a little itty bitty point. Okay.
Mm-hmm.
And this is a cube, and there's fancy terms. They call it a differential volume element.
Mm-hmm.
But on the face of this, on this green cut face, this is a unit area.
Mm-hmm.
So if I multiply the stress by 1, it gives me a force, right?
Mm-hmm.
And so essentially what I have is, I have on this face 5.57 megapascals. Yeah.
Mm-hmm.
Okay. And I can draw the other sides of the cube right here. So if I could turn this cube around,
Mm-hmm.
right? Do I have a cube somewhere? I have lots of cubes. I have, this could be a cube, right?
Mm-hmm.
So here's the green face,
Mm-hmm.
right here. Okay. This whole thing has to be in equilibrium, but I can only have stresses or forces that are parallel or normal to these surfaces. Okay. And so then I need to be in equilibrium. So that means on the opposite side of this,
Mm-hmm.
I have an equivalent stress that's pointing up
Mm-hmm.
to create that balance, 5.57 megapascals in the back.
Mm-hmm.
And now this thing is rotating freely in space. If I took moments about this axis is rotating freely.
Mm-hmm.
And so I need, on the top surface, I need a shear stress here. And then on the bottom surface, I need a shear stress here
Mm-hmm.
to keep it in equilibrium. So I have to have some of the forces in the horizontal equal to 0, some of the moments equal to 0, and this. And the reason the arrows kind of meet together
Mm-hmm.
is that if I were to look at a side view as an observer, let's say standing right here,
Mm-hmm.
looking like this is what I would see. I would see here's the cube, here's the green face,
Mm-hmm.
yeah, and my stresses on this surface, 5.57, on the bottom, 5.57, the top, and all these stresses are 5.57 MPa.
Mm-hmm.
I have only shear stress. This is a condition of pure shear. So my deformation should look, my deformation of this volume will look, probably exaggerating this right here, like this.
Yeah.
Does that make sense?
Uh-huh.
Yeah? Yeah, so check out this book. Where's the book? So here, if I have shear, it's doing that. And it's a pure shear, the deformation. And then we could do strain calculations, but it's all good.
Yeah.
Okay. All right. And so that's okay. But if you don't understand the differential volume element thing right now,
Mm-hmm.
it's okay. We're gonna review it a lot more. We're gonna do it a lot more later.
Okay.
But when the loading gets more complicated,
Mm-hmm.
we're gonna have that. But this is essentially it. The process is, just like axial loading, internal loading, calculate stresses.
Mm-hmm.
And that's it. And the end. Bye-bye. Wow.